Hello friends, here in this video we will see a problem on calculation of stresses for a T section. Here we have a question. A T column of cross section as shown in figure, the diagram is given, is subjected to compressive load at point C as shown in figure. Here the compressive load is there and its value is 100 kilonewton. Find the stresses produced at point A and C. It means here we have to calculate how much stress is at this point A and at point C. So these are the question for us. Now in the data here we have a diagram. In this diagram, as we can see, the T section is having width of 400 and then its overall depth is 400. If I look at the upper flange, the width is 400, depth is 100. For the bottom flange, this is called as the web. For the web, width is 100 and depth is 300. So here the question is to calculate stress at A and stress at C. So these two questions are there which we have to solve, and for that purpose what we will do is, for the T section which is given, simply divide this into two rectangles. This would be rectangle 1 and here we have rectangle 2. Now starting the solution for this problem. Since area 1, which is for me the area of web, it is 100 into 300, so that is 30 into 10 raised to 3 mm square. Then area 2, which is 400 into 100, it is 40 into 10 raised to 3 mm square. Now from this I'll get the total area of T section by adding A1 and A2. So therefore total area is A1 plus A2. A1 30 into 10 raised to 3, A2 40 into 10 raised to 3. So therefore capital A is 70 into 10 raised to 3 mm square. After getting the total area, the next thing would be to locate the centroid for such kind of a problem. If they give T section, I section or any other C section, then in that case we need to know the location of centroid. So here I'll say that since location of centroid with respect to y-axis, that is given by x bar is equal to, and this x bar indicates the location of y-axis, and that is 400 by 2, which is 200 mm. Then here I have to even calculate y bar, because we know that since T section is symmetric about y-axis, therefore centroid will be there on this y-axis, but at which distance that we don't know, and for that we require y bar. So here I'll say that therefore location of centroid with respect to x-axis, it is given by y bar is equal to A1 into y1 plus A2 y2 divided by A1 plus A2. So here we have the formula of y bar. Next, therefore here I'll say that all the values A1, A2 and this total area are known except y1, y2. So we will get y1 as, y1 is the x-axis for the given rectangle 1 and its x-axis will be passing through half of 300, axis 1 1. So here we have y1 as half of 300, that is 150 mm, and y2 will be the x-axis for second rectangle, So this x-axis is, first of all, there is 300 distance, so 300 plus at half of 100, so this is 350 mm. So therefore I'll keep this as equation 1, put all values in equation number 1. So here we have y bar is equal to a1, it was 30 into 10 raised to 3 into y1 150 plus a2 40 into 10 raised to 3 y2 350 divided by a1 plus a2, total area 70 into 10 raised to 3. So from this I am getting the value of y bar as 264.3 mm, and as I have taken all the distances from bottom, so this reference is from bottom. Similarly, I'll get the distance from top, that is, here we have 300 plus 100, that is 400. From that, if I subtract 264.3, I'll get the value as 135.7 mm. This is from top. So here is the location of x-axis, which is denoted by y bar. 264.3 mm from bottom. So here this distance I am marking it as 264.3 mm. This is the location of x-axis from bottom, and from top it is 135.7 mm. So here I have located the x-axis for the T section. Wherever x and y intersect, that is the centroid. So centroid has been located. The next thing, as we have to find the stresses at point A and C. At C the load is 100 kilonewton, so load P is 100 into 10 raised to 3 Newton. Now as we see, the load is eccentric with respect to the centroid, so there will be direct as well as bending stress. So because of direct stress, I'll write down after this. Now since the load is eccentric, it means at a distance from the centroid, so therefore there will be direct as well as bending stress. So therefore I'll write down direct stress sigma d is equal to load upon area. So now here I have written the formula of direct stress, which is load upon area. So therefore sigma d is equal to, load is 100 kilonewton, so 100 into 10 raised to 3 Newton, total area is 70 into 10 raised to 3. So from this I'll get the answer of direct stress as, it is 1.428 Newton per mm square, and this direct stress is of compressive nature. After getting the value of direct stress, the next thing would be to calculate the bending stress. And to calculate the bending stress, first I'll write down. Now in order to calculate the bending stress, we should know the MI, that is moment of inertia, about x-axis for the complete section. Since MI about horizontal centroidal axis, it is given by Ix6 is equal to Ix61 plus Ix62. Keeping this as equation second. So therefore Ix61 is the moment of inertia for the first rectangle but not about its own axis, but about the centroidal axis xx. So here we have Ix61 as Ig1 plus area 1 into h1 square, and this is by parallel axis theorem. Now if we see here, the x-axis of rectangle number 1, it is at a distance of 150 mm from bottom, but the x-axis of complete section is 264.3 mm from bottom. So there is a gap, there is the distance between the axis, and that distance is called as h1. So here we have Ix1 is, Ig1 is the moment of inertia for rectangle 1 about its own horizontal axis, and that is BD cube by 12 plus area 1, we have found out it was the value of 30 into 10 raised to 3. Now h1, that is 264.3 minus 150 whole square. So here Ix1, here I'll put B and D. B is 100 and D is 300 for the first rectangle. 100 into 300 cube divided by 12 plus 30 into 10 raised to 3, and this value, it is 100, and here we have 114.3 whole square. Calculating this throughout, I'll get Ix61. So therefore Ix61 is 616.93 into 10 raised to 6 mm raised to 4. Now after getting Ix61, I have to calculate Ix62 here. So therefore Ix62 is also Ig2 plus area 2 into h2 square, again by parallel axis theorem. So therefore Ix62 is Ig2 BD cube by 12, area 2 40 into 10 raised to 3, h2. Here we have the x-axis of rectangle 2 and x-axis of the complete section is at 135.7 mm from top. So this distance between the two axes, that is h2. So it is 135.7 minus, from 135.7 I'll subtract half of 100, that is this distance, which will give me h2. So minus 100 by 2. Here for the second rectangle, B is 400, D is 100. Calculating this throughout, I'll get Ix62, which is 327.11 into 10 raised to 6 mm raised to 4. After getting Ix61, Ix62, I'll say that put Ix61 and Ix62 in equation number second. So therefore we have Ix6 is equal to, in equation number second, there we had written Ix6 is Ix61 plus Ix62. So putting their values, Ix61 was 616.93 into 10 raised to 6 plus Ix62 327.11 into 10 raised to 6. So therefore here I'll get Ix6 as 944.04 into 10 raised to 6 mm raised to 4. Now after getting Ix6 value, the next step would be to calculate the bending stress, and for that we require bending moment also. So first here I'll say that therefore bending moment M is given by load into eccentricity, and here if we see in the problem, it is given that load is at point C So it is at a distance of 264.3 mm from the centroid we have to take as the reference. So 264.3, this becomes the eccentricity and load is 100. So here I'll write down 100 into 10 raised to 3 into 264.3. So bending moment, that value comes out to be 26.43 into 10 raised to 6 Newton mm. Now, after getting the bending moment, as I see in the question, there are two things asked: stress at point A and stress at point C. So for that, we would be requiring individual bending stresses, because the magnitude of bending stress will change depending on the value of y bar. So here I'll say that, therefore, bending stress at point A, that is sigma B A, is equal to, the formula is m upon I into y, that is from the flexural equation. Here I'll write down, this formula has come from flexural equation. So therefore, the bending stress at A will be bending moment 26.43 into 10 raised to 6, I 944.04 into 10 raised to 6 into y. Now for point A, we should know the distance from the centroid up to point A, and that is 135.7 mm. So here I'll get the bending stress at A, and my answer is 3.80 Newton per mm square. Now, after getting this bending stress, here we can say that we have found out the bending stress at A. The next thing, direct stress also we have got. Now I'll say that, therefore, after this, resultant stress at point A is equal to direct stress minus bending stress. Why I am subtracting? There is the reason for that, and the reason is load is at point C and it is compressive load. From point A, the load is located at some distance. So when the load is acting, there will be C which is going to get compressed, whereas A would be lifted. So there is tensile stress at A, and in this chapter we take tensile stress as negative. So here it is sigma D minus sigma B. So now, therefore, the resultant stress at point A is equal to stress at A, sigma D 1.428 minus sigma BA 3.80. So the value comes out to be minus 2.371 Newton per mm square. This will be the first answer, because in the problem they have told to calculate stress at A, and here I am getting negative. It means the stress is of tensile nature, because in direct and bending stresses we take tensile stress as negative, compressive stress is taken as positive. So after this, in a similar manner, bending stress at point C, that will be sigma bending suffix C is equal to m upon I into y, again by flexural formula. So therefore I'll go on putting the values here. The bending stress at C, bending moment 26.43 into 10 raised to 6 upon I 944.05 into 10 raised to 6. Now y value, when we are considering point C, at that time y we have to take it as 264.3 mm, because this is the eccentricity for C. Eccentricity for A was 135.7, so this was y value for A, this is the y value for C. So 264.3 0.3. So here I get sigma BC, bending stress at C, that comes out to be 7.4 Newton per mm square. After getting the bending stress at C, I can calculate, therefore, resultant stress at point C, that will be direct stress plus bending stress, because on C, when the load is acting, the load is of compressive nature, so it will compress at point C. So stress at C is equal to direct stress, it was 1.428 plus bending stress 7.4. So from this, the value of sigma C, it comes out to be 8.828 Newton per mm square. And as I am getting this answer as positive, it means that it is compressive stress, because in this chapter we take compression as positive. So here in this video we have seen how to calculate the stresses at two given points, that is A and C. At A it was of tensile nature, at C it is of compressive nature, and with this we complete the problem.